Good evening, ladies and gentlemen. I hope you had a good weekend. I appreciate everybody sticking along with the class so far, and hopefully, we'll have a productive week next week. I wanted to get us started a little bit on a thing from chapter 11. It's probably the only thing from chapter 11 we're going to touch base on. The rest of the material is a mixture of things that we have already gone over and some stuff that's a little more advanced, probably more appropriate for my Chem 2 class. We're going to mostly focus on chapter 12. So here's a little bit from chapter 11. This is what's called a phase diagram, and this is getting us back into the idea of physical properties of matter, of solids, liquids, and gases, before we get into chapter 12 for this week, which is exclusively gases. So some of you may remember our energy ramp here that we had, where we were dealing with specific heats of substances. And we would take a substance from a solid to a liquid to a gas, through melting and then boiling, and then we would look at possibly the energy that would be required to leave to get a gas to cool down to a liquid and then cool down to a solid. And we learned that much of the energy that is invested either in heating or cooling occurs at these 2 points, which are called the heat of fusion and the heat of vaporization. If we're warming up a solid to a liquid, we have to put in tremendous energy investment to kind of weaken those intermolecular forces between the molecules of water or molecules of carbon or whatever it is that we're looking at, and bring it to melting, turn it into a liquid. And then if that liquid is going to condense into a solid, then that same amount of energy has to leave at the same clip. Whereas in this direction, we're adding energy, and in this direction, energy is leaving the system. Similarly, you bring a liquid to a gas, there was even more energy. Almost, in the case of water, about 8 or 9 times more energy it takes to go from a liquid to a gas. It was called the heat of vaporization. And so if we're going from liquid to gas, we'd call that moment boiling, and then gas to liquid, that'd be condensing. So there is a related type of diagram that we're getting into called a phase diagram. And what this does is this brings in the idea of pressure as a driver of what state that a substance may be in, along with temperature. And so a lot of natural forces are often viewed in terms of temperature and pressure. When we get into gases, it's going to be a matter of temperature, pressure, the gas's volume, and the number of molecules all interacting. So here, what this does is this kind of maps out what state a substance is based on its temperature and pressure. So, let's say that we're measuring temperature. Let's say we start at an absolute zero, which we can't experience on Earth, and probably hasn't been truly experienced, but we just kind of imagine it exists. And so, we're having temperatures going up, say maybe in the hundreds. And so this may be something like one of the, maybe not, if not a noble gas, something that's gas under a lot of conditions, like carbon dioxide or something. And then we may measure the pressure like in atmospheres. So like air pressure, near the sea level of Earth is, about 1 atmosphere. So we're just going to kind of come up with a few crude numbers here. This will be in hundreds. And so if I was saying, I wonder what this substance would be if it's a solid, a liquid, or gas, or if it was at double the atmospheric pressure on Earth and the temperature were at, say, 50 degrees Kelvin, well, it's going to be a solid. But if we were at that atmosphere, if we were at that pressure, and we raise the temperature up to 200, it would be a gas. Or if we kept the temperature at 200 and raised the pressure, we went up, like to, say 2.5, it would be a liquid and so forth. So basically, if you have a known pressure and a known temperature, you can place that point where the two factors meet, and we can see what state of matter it would be in. So how does it relate to this chart? Well, if you'll notice, I've color coded these zone lines that separate solid, liquid, and gas. And you'll notice that I have green also being the heat of fusion, and that makes sense because the heat of fusion is the line that separates the solid and the liquid world. Whereas over here I have blue representing the heat of vaporization, and as you can see, this line separates the liquid and gas zone. Now what about this funny line, this red line? Well, that separates solid and gas. So when can a solid go straight to a gas or gas go straight to solid? The most well-known example you can buy if you're at least 18 at a Publix or some other grocery store called dry ice. It's carbon dioxide. And it undergoes what's called sublimation. That's a transition straight from a solid to a gas without experiencing a liquid phase. So this would be a case where if we maybe took a substance at moderate pressure and very low temperature, and then suddenly dramatically raise the temperature without raising the pressure, we would go straight from a solid to a gas. Or if we had, in this case, we had a substance that was being kept at, say, room temperature on planet Earth, 300 Kelvin, which is about 25 degrees Celsius, and then we just and had it at Earth's pressure, which is 1 atmosphere, and then we just dramatically drop the temperature very fast while keeping the pressure the same. It would undergo what's called deposition. It would go straight into a solid and bypass the liquid phase entirely. And there are many substances that never go through a liquid phase under a lot of conditions because either the pressure is too low under the conditions, or they're at a certain region temperature-wise with a lower pressure, that liquid phase just simply isn't experienced. So, like I said, the most well-known example on Earth, you have to kind of manufacture, which is, carbon dioxide put into a solid state. It is very hard to get it in a liquid state. It has to be at a certain range of temperatures and a certain range of pressure. And not surprisingly, on a lot of these phase diagrams for different substances, they are often most of their zone is gas or solid. Often the liquid is the smallest region in the chart. But what if we were at a point where all three phases met? We would be at what's called a triple point. And a triple point is where all three phases are in equilibrium. And so that is a little activity we're going to try to do this week. I'm going to try to demonstrate with dry ice where you can see carbon dioxide in a solid, liquid, and gas form. And then we have this very mysterious zone over here, the supercritical fluid. And this is always the upper right of a phase diagram. And it's a region where the pressure is extremely high and the temperature is extremely high. And it's so much so that the substance does not behave completely like a liquid, or it behaves, it's too hot to act as a liquid, but it's too pressurized to act as a gas. So it exhibits properties of both. And so thus we have this zone, which is always reserved for the upper right regions of a phase diagram chart, the supercritical fluid. So in recapping real quick, there is an analogy between the this type of specific heat diagram and the phase diagram. The main difference is that the specific heat, we can look at it linearly because it's only viewing the temperature. There isn't another factor to measure against. In this case, we were always assuming that the pressure was constant, usually standard room pressure conditions. It's only the temperature that we're manipulating. Whereas here, we're able to look at the effect and the of temperature and the pressure. And that allows us to get a much better sense about the kinetic behavior of this substance and in what phase we perceive it as, mostly as a solid, liquid, or gas, or under these extreme conditions, a supercritical fluid.